second day of Gian workshop on biocomposites. Now let us begin today's session. I invite Professor Alain Dufresne to deliver his valuable lecture on polysaccharide nanoparticles. Over to you, sir.
We'll continue today, but move a little bit to something which is related, of course, to biocomposites, but more on the nanoscale. And first, we'll see how we can prepare nanoparticles using polysaccharide, so cellulose, of course, but also chitin and starch. So we have seen yesterday that there are some limitations in the use of natural fibers, mainly related to the hydrophilic character of these fibers that result in a poor adhesion with a hydrophobic polymeric matrix and a poor dispersion. There are also some issues that can be related to the thermal stability of these natural fibers, but another drawback is the big variation of the properties of these natural fibers. The properties, or the chemical composition and the physical properties of this fiber depend, of course, on the source of cellulose, but also climatic condition, maturity of the plant, type of soil, and so on. And so it's difficult to control the properties of these natural fibers. One idea to avoid this drawback is to eliminate the macroscopic flows, and for this it's necessary to disintegrate the natural fibers and separating nanoparticles which are almost defect-free. So you remember the composition of cellulose, of natural fibers, consists of cellulose, which is a structural element, and it is surrounded by a matrix composed of lignin, and hemicellulose acts as a compatibilizer between these two materials. Usually, purified natural fibers are used, so cellulose fibers are used, so meaning that the first step to obtain nanoparticle consists in the removal of lignin and hemicellulose, and then these cellulose fibers have this structure. They consist of filaments, and these filaments consist of aggregate nanofibrils. You can see these nanofibrils, which are aggregates through hydrogen bonding, of course, and these nanofibrils consist of alternating crystalline and amorphous domains. So from these cellulose fibers, there are mainly two options to extract nanoparticles. The first one is a mechanical treatment. So the objective is to submit this cellulose fiber to a strong shear action in order to progressively release more or less individual nanofibrils. The second option, or the second strategy, is a chemical treatment. In fact, it's an acid hydrolysis treatment that consists in the selective dissolution of amorphous domains. And so we can obtain a different kind of nanoparticles that we will show later. First, I would like to share with you a short video that has been proposed by TAPI, the Technical Association of Pulp and Paper Industry, about 10 years ago, that show these different types of nanoparticles.
Searching. The forest products industry is constantly searching for ways to unlock incredible innovations. And where are we searching? Everywhere, but especially in a place that we know well, the forest. We've been making useful products from trees for years, but now we're going even deeper into the tree for a new generation of products. Using the science of nanotechnology, we're unlocking the tiny secrets nature has held for centuries. But why are we doing this? Because trees have so much to offer. Trees and plants are sustainable, renewable materials. They give us shelter, oxygen, and remove carbon dioxide. Trees also are the source of more than 5,000 products you depend on every day, like lumber for homes, furniture, heating, tools, airplanes, and even some of the food we eat. Trees give us paper, packaging, medical products, and other items used every day for home, school, work, and play. And the fibers that make up the tree also are used to help make other products you use every day better. Trees even help us make biofuels, an alternative fuel that can help lessen our dependency on oil. But we've only just scratched the surface. As we go deeper into the tree, we find even smaller fibers that have special properties to make products better. Properties that make products more durable, lighter, stronger, thinner, smoother, more water resistant. But we're not stopping there. Using new scientific tools, we're uncovering even smaller fibers called nanocellulose. These fibers will be used to make products better in such applications as automobiles, aerospace, defense, and others. And today, we are learning to use the smallest component yet, cellulose nanocrystals. Stronger than metals and very light, this special material is the key to unlocking new high-tech materials. Materials that people are just beginning to imagine. We're searching. And why are we searching? Because we have an abundant, renewable resource with the potential for as many products as we can imagine, and maybe even more. The world continues to demand more sustainable products, and the forest products industry is searching for ways to deliver them, just like we've done for centuries. Nanocellulose. Rethink trees.
And so there is a definition for a nanoparticle. It's a particle which has at least one size or one dimension between 1 and 100 nanometers. So we can consider different geometries. In the case of spherical nanoparticles, of course, the representative dimension is the diameter that should be lower than 100 nanometer. In the case of platelet, the critical dimension is the thickness that should be lower than 100 nanometer. And in the case of fibers, like for example, carbon nanotubes, the critical dimension is the diameter that should be lower than 100 nanometers. So I will show you briefly the main features or common features of the three polysaccharides that we will use to extract nanoparticles: cellulose, starch, and chitin. So in the case of cellulose, we have a hierarchical structure, which is the same for the other polysaccharide, meaning that we can see this material at different levels of observation from the tree. So the representative scale is the meter, and we can decrease or observe closer this material up to vessel and luminas, which is in the order of a millimeter, the cell wall that we described yesterday. And remember that in this cell wall, we have some fibrils, or cellulose fibrils, which are aggregates of nanofibrils, and then we can separate these nanofibrils, which are typically between 1.5 and 3.5 nanometer in diameter. And so this material, cellulose, is associated with hemicellulose and lignin. We have seen this slide previously. So it represents the hierarchical structure of cellulose fibers. Sorry. And it is the same for chitin, which is another polysaccharide. So it looks like cellulose, but there are some difference regarding the side groups. Chitin is also a structural element, meaning that in nature it provides the mechanical properties to the living organism. But it is not found in plants, it is in the cell wall of fungi, in the exoskeleton of arthropods like crabs, lobster, shrimps, and insects, and can be found also in the beaks of cephalopods like squid and octopus. It is also an abundant polymer. It is the second most abundant polysaccharide after cellulose. So starch has also a hierarchical structure. So I'm sorry I didn't describe the hierarchical structure of chitin. So because chitin is a structural element, it means that it is found in nature in the form of fiber. As soon as mechanical properties are involved, the material is in the form of fiber. Except that in this case, and compared to cellulose, the matrix is not composed of lignin and hemicellulose, but it is composed in this case of proteins. So in the case of starch, the function in nature is different. It's not a structural element. It's what is called a storage polymer, meaning that for sure the form or the shape of this material will be different. You know that starch can be extracted mainly from tubers, cereals, and beans. And in this material, the starch occurs as partially crystalline or semi-crystalline microscopic granules. You have some example of starch granules here from different sources of starch. And so it's not perfectly spherical particles, but the dimension roughly range from 1 to 100 micron. And when cutting one of these starch granules and performing a light hydrolysis, we have this structure, an onion-like structure. And this structure consists of alternating crystalline and amorphous domains. So meaning that as chitin and cellulose, starch is a semi-crystalline polymer, and it also has a hierarchical structure, which is represented here. So for example, in the case of corn, we found starch in the form of granules. These granules consist of alternating crystalline and amorphous domains, and in this crystalline domain, we found smaller entities which are called blocklets, and these blocklets consist also of alternating crystalline and amorphous domain. So starch is not really a pure product. It consists mainly of two macromolecules, amylose and amylopectin, and the content of each macromolecule depends on the source of cellulose. It's in fact the same macromolecule, except that amylose is a linear macromolecule and amylopectin is a branch macromolecule. So, from this polysaccharide, you can extract nanoparticles following two strategies, a mechanical strategy or a chemical strategy. For the mechanical strategy, remember that the objective is to submit the material to a strong shearing action in order to release individual components, like, for example, cellulose fibrils. So different equipment can be used. I will not describe all this equipment, maybe only this one, which is the oldest one, because it was used during the first publication on the processing of this kind of material in 1983. It is the homogenizer, which is classically used in food industry. So typically, a fiber pulp is used, a dilute fiber pulp. It's typically 2% suspension, and this suspension is pumped and forced to pass through these very thin slits, and this gap, or the thickness of this gap, change the function of time because of the movement of this valve. And when the dispersion, when the fibers pass in this very thin slit, they are submitted to strong shearing action. And so progressively, after several passes, we can obtain a more or less fibrillate material. So some other equipments can be used. These are some other equipment that can be used: ball milling, ultrasonication, steam explosion, twin screw extrusion, so which are more marginal, let's say. And this is the aspect of the material which is obtained after this mechanical treatment. This is a suspension of eucalyptus fibers after this fibrillation or this mechanical treatment, and the solid content is 2%. So it means that there are 98% water. And you see the aspect of this suspension. It's a viscous gel with a shear thinning behavior. And this suspension is stable. And in the case of this treatment, the mechanical treatment, the stability comes from residual hemicellulose at the surface of the nanoparticles. If we get closer, we see the aspect of this gel. So it consists in very long and flexible filaments. You can see some aggregates, some more or less individual nanofibers or nanofibrils also. Of course, it depends on the source of cellulose. It depends on the severity of the treatment also. So, as I told you, this was discovered in 1983, but it was a lab curiosity because the main problem for any application is the high energy demand. So the energy demand is very high to obtain this kind of material, meaning that some pretreatment has been proposed in order to reduce this energy demand. So it can be an enzymatic hydrolysis or it can be a chemical treatment. Now, regarding this material, the yield is almost 100% because the nanofibrils are just separate. The width of this nanoparticle or these filaments range from 2 to 100 nanometers, so it depends on the mechanical treatment. But as you can see, the length is very difficult to determine. So there are some papers that suggest some experiment to at least estimate the length of these nanofibrils. So, pre-treatment, so it can be an enzymatic hydrolysis. I will not go into details, but different types of enzyme can be used. Endoglucanase that randomly cleaves the molecules of the cellulose chain. Hexoglucanase that mainly attacks the end of the molecule of the fibrils, sorry, and beta glucosidase that break down cellulose into glucose monomers. A cocktail, of course, of this enzyme can also be used. So the objective, of course, is to reduce the length of the fibers to facilitate the extraction. Now, regarding the chemical treatment, different treatments have been proposed, and all these treatments aim to introduce some charge at the surface of the molecules in order to have a repulsion and to facilitate the separation of the nanofibrils. So the most well-known is the tempo oxidation treatment, which is briefly reported here. In fact, in this case, as you probably know, the 6 carbons, or hydroxyl, sorry, are the most reactive, so meaning that they are converted, in this case, into carboxylate groups, which are here, and which are negatively charged, meaning that the release of the fibril is easier. So some other chemical pretreatment has been proposed. I will not describe everything. Carboxymethylation, carboxylation, and you can see that in each case, negative charge are introduced, sulfonation, phosphorylation, and periodate oxidation. So now, regardless of the source of cellulose, the aspect of the nanomaterial is always the same. It consists of very long filaments, flexible filaments, consisting of more or less individual cellulose nanofibrils. And you can see that any kind of, or any source of cellulose can be used. Some, let's say, exotic source. You can see garlic skin. Why not? It contains cellulose, so it's a byproduct. And so at the beginning, it was difficult when a new material is introduced to find a terminology. So it means that different terms have been used to describe this nanoparticle, cellulose nanoparticle obtained by a mechanical treatment. So I report here some of this denomination. And finally, TAPI has decided to use cellulose nanofibrils to describe these nanoparticles obtained from cellulose biomechanical treatment. So we can have an idea about the degree of fibrillation of these nanoparticles following different parameters, which are reported here. The turbidity of the suspension, in fact, it becomes more transparent upon fibrillation. The viscosity of the suspension increases. The water retention increases. The porosity of the film that can be obtained by casting evaporation decrease, and then the density increase. The mechanical strength of the film increase. The degree of polymerization decrease. The specific surface area, of course, increase. And for the degree of crystallinity, sometimes it increases, sometimes it decreases. So, regarding the turbidity of the suspension, it becomes more transparent. You have some example here. I don't remember which kind of cellulose it was. Maybe eucalyptus. Yes, it was eucalyptus. And this material, so these eucalyptus fibers, were submitted to different pretreatment and different mechanical fibrillation action. You see a number here that refer to the strength of the tempo oxidation treatment, meaning that when this number increased, the tempo oxidation was more performant, so meaning that we can expect easier fibrillation. And from 1 to 4, you can see that the change is in the number of paths in the during the mechanical treatment, meaning that the fibrillation should increase from the left to the right. So it's not easy to see the turbidity of the suspension from this figure, but we can determine the transmittance. You can see here for, I don't remember, yes, it was after 5 or 6 pass at 300 bar, the different sample with different severity in the pretreatment. And what you can see is that when increasing the severity of the tempo oxidation treatment, the transmittance increase, meaning that the material is more fibrillate. Here, you can see some other sample, and what is observed here is that when the number of passes in the homogenizer increases, the material becomes more fibrillate, and the transmittance of the dispersion increases. Viscosity of the suspension, it increases. You can see here G prime. G prime corresponds to the storage shear modulus. So it's more or less equivalent to the viscosity of a suspension as a function, as a function of the concentration of cellulose nanofibrils. And you can see a huge increase in the viscosity. So you can see that here it's a logarithmic scale. So it means that for only few percent, we have an increase in viscosity of several decades. Here we can see G prime, the storage shear modulus, and G double prime, which is the loss storage modulus, loss shear modulus, sorry. And we can see the evolution of the frequency of the measurement. So usually when considering a liquid, G double prime is higher than G prime. G prime, sorry. So here for different concentration, we can see that for the highest concentration, G prime is higher, meaning that it is a gel, it's not a liquid. When decreasing the concentration, we can see that depending on the frequency of the measurement, we can have a gel or we can have a viscous liquid. Water retention, it increased. So water retention represents the ability of the fibers to take up water and to swell. So there is a protocol to determine this parameter, which is well known in the pulp and paper industry. The degree of polymerization of cellulose decreases because, of course, the material is submitted to a strong shear action, meaning that we can break some macromolecules. But it also depends on the pretreatment that has been used. You can see here, for example, the degree of polymerization of cellulose nanofibrils using, the function of the stage, using two different pretreatment, carboxymethylation and tempo oxidation. So you can see that tempo oxidation result in a strong decrease in the degree of polymerization. Now the specific surface area, of course, it increased because it corresponds on the surface corresponding to 1 gram of material, of the ratio of surface to volume. This specific surface area can be determined by different techniques. So usually absorption of different gas are used. So it's a problem with cellulose nanofibrils because it's necessary to use a dry material. And of course, when drying cellulose nanofibrils, they tend to aggregate, so which decrease the specific surface area. You can see here the evolution of the specific surface area as a function of the homogenization energy or the severity of the treatment. It increases, and you can see that then it stabilizes because no further fibrillation can be obtained. Crystallinity. Sometimes it increases, sometimes it decreases. What is the reason for this? We can imagine that during the mechanical treatment, we can easily break the amorphous domain, meaning that the degree of crystallinity should increase. But of course, some crystalline domains are also damaged during this mechanical treatment, meaning that the degree of crystallinity can also decrease. So you probably know that usually for polymers, the degree of crystallinity is determined by differential scanning calorimetry. We cannot use this technique with cellulose. Why? The reason is that to determine the degree of crystallinity from DSC experiment, it's necessary to melt the material. And cellulose cannot be melted. So meaning that there is a limitation in the number of techniques that can be used, and usually X-ray diffraction is used. And you have here some X-ray diffraction pattern corresponding to different sources of cellulose. So this is for purified cellulose, and this is for the nanofibers or nanofibrils that have been extracted. So from this X-ray diffraction pattern, it's possible to determine what is called a crystallinity index from this equation. And so this parameter here corresponds to the magnitude of this strong peak here. And the second parameter corresponds to the intensity of the diffraction pattern in this valley here, which is associated to the amorphous part of the material. This equation was used to determine the crystallinity index of these different materials for wood, rice straw, potato tuber, for purified cellulose, and for nanofibers. And you can see that in this case, the mechanical treatment results in an increase in the crystallinity of cellulose. This is another example in which you can see that first, During fibrillation, the crystallinity increases because of the destruction of amorphous domain, and then it decreases. Because when using a higher shear rate or stronger shear rate, some crystalline domains can be damaged. It is also the case for the diameter of the crystals that progressively first increase and then progressively decrease. So now regarding the mechanical properties. As you can imagine, the determination of the mechanical properties of individual nanofibrils is difficult to perform. There are some data that have been reported, so it can be obtained by calculation or experimentally using Raman spectroscopy or atomic force microscopy. In atomic force microscopy, so maybe I will use a blackboard here. We use a substrate with some grooves like this, and the nanofibrils are deposited on this surface, hoping that one nanofiber can be like this, and then with the AFM tip, it's possible to exert a force, like for a three-point bending test. And from this, it's possible to evaluate or estimate at least the stiffness or the modulus of the material. The average value is around 1 gigapascal. It's a high value. Because for glass fibers, for example, the modulus is around 70 gigapascal. We have a higher value in this case. So films can be obtained from this cellulose nanofiber or nanofibril dispersion just by a casting evaporation technique. So you experiment this yesterday afternoon. And you see the aspects of these films which are called nano paper, because of course it's like a paper except that it's not lignocellulosic fiber, but it's cellulose nanofibrils. And when performing tensile tests on these films, we can see that depending on the degree of polymerization of the nanofibrils, we have different behavior. So the modulus, which is the slope, the initial slope of the curve, remains similar, but you can see that when decreasing the degree of polymerization of the nanofibrils, there is a decrease in the strength, the stress at break, and in the elongation at break of the material. Typically, the modulus of this nanopaper is around between 1 and 20 gigapascal. So, of course, it depends on the condition of the measurement. It depends also on the preparation of the film. If it is obtained just by evaporation or by hot pressing, the density varies, of course, and the mechanical properties vary. You can see here the evolution of, as a function of the relative humidity of both, this is the loss angle, which is obtained by dynamic mechanical analysis, and the storage modulus. So for the loss angle, there is not so much change because no relaxation can be observed, but for the modulus of the material, when increasing the relative humidity, when increasing the water content, you can see that the stiffness of the nanopaper decreases. Because, of course, these water molecules can interact with the cellulose fiber, and it limits the interactions between the cellulose nanofibril and then the strength of the material, of the nanopaper. So the second option is chemical treatment. So it's an acid hydrolysis which is performed, and any kind of strong acid can be used. The objective of this acid hydrolysis consists in a selective dissolution of amorphous domains of cellulose. So these amorphous domains that link the crystalline domains in the nanofibril can be dissolved, but depending on the nature of the acid which is used, the surface chemistry can be different. Usually, sulfuric acid is used. The reason for this is that sulfate groups are introduced at the surface, and these negatively charged groups promote some repulsion between the nanoparticle, and it means that the suspension is stable, which is not the case when using hydrochloric acid. So you have here the different steps of the process to obtain these nanoparticles. So start from natural fibers with some treatment in order to remove non-cellulosic material, and then it is submitted to this hydrolysis treatment. So typically, the duration of the treatment is 45 minutes. The temperature is, let's say, around 50 degrees, and the acid concentration is 54 to 65%. But of course, it needs to be adapted depending on the source of cellulose. And then, after this acid hydrolysis, that remove this amorphous domain that link the crystal in the fiber, a purification step is used just to remove the free acid. A mechanical treatment, sonication, is applied to separate these nanocrystals, and so these nanoparticles are then obtained. Sorry, I didn't just. Yes, the stability in water is due to the surface sulfate group, as I mentioned previously. So the characteristic of these nanoparticles, which are called cellulose nanocrystals, depend on both the origin of cellulose and the hydrolysis condition. So typically the yield, so depend on the cellulose content, of course, and the crystallinity of cellulose is between 20 and 80%. The width of these nanoparticles is from 5 to 30 nanometer, and the length range from 100 nanometer to 1 micron. You can see that these nanoparticles, so previously we obtained flexible filaments. In this case, we obtained straight rod-like nanoparticles, which are highly crystalline. In this case, it's for cellulose nanocrystals extracted from rami fibers. You can see here the evolution of the length of the crystal as a function of the duration of the hydrolysis treatment. It decreases and then it stabilizes. So again, different terms have been used to describe this kind of nanoparticle obtained from cellulose by an acid hydrolysis treatment, and finally, cellulose nanocrystal should be used. And you can see that for different sources of cellulose, the aspect is very similar. It's always rod-like stiff nanoparticles. So some other examples, different sources of cellulose, and here again. There is another type of cellulose nanoparticles or cellulose nanocrystals. So two previous ones, so cellulose nanofibrils, cellulose nanocrystals, have been obtained by what is called, I don't remember, top-down, strategy, meaning that we start with microscopic objects or particles, and the size is decreased. It's possible to obtain nanocellulose from a bottom-up approach. You probably know bacterial cellulose, which is produced by some bacteria, just using a substrate that contain sugars. And so this bacteria electrospin cellulose or nanocellulose in the form of filaments. So the most well-known example are the vinegar mother, kombucha tea, and nata de coco, which is made from, that consists of bacterial cellulose. So it's like a membrane consisting of these very long filaments. So chitin can also be used to prepare these nanoparticles. Biomechanical treatment. Here we have chitin nanofibril films obtained from black tiger prawn or from the shell black tiger prawn. And nanocrystals can also be used, can be obtained, from chitin. The same story. it's an acid hydrolysis treatment that selectively dissolve the amorphous domains from chitin. You have some example here of nanocrystals obtained from squid pen, crab shell, shrimp shell. In this case, the dimensions are very similar to what is obtained for cellulose in the case of wood. This guy, Gopaladner Kalaprasad, was a postdoc coming from Kerala, so you can see that he was working with me a long time ago, and he will come very soon in 1 or 2 hours. Yes, this is another source of chitin, which is more exotic, let's say. It's Riftia tubes. Riftia tubes are these tubes in which there is a worm. It can be more than 2 meters long, and you can find these worms or these tubes in the deep sea, 3,000 meters deep. Of course, at this level, the pressure is very high, meaning that the chitin material is highly crystalline. And you can see the resulting nanocrystals. They are very long. So the average length was 2.2 micron, and the average diameter was less than 20 nanometers. So now starch can also be used and can also be submitted to an acid hydrolysis treatment to extract or to isolate the crystalline domains of starch. Remember, starch is in the form of microscopic granules, which are more or less spherical. And you can see here the evolution of the dispersion during the acid hydrolysis treatment. You can see here, in fact, in white, the crystalline domains. During the acid hydrolysis treatment, the crystalline domains are perpendicular to the screen because these nanocrystals are still linked by amorphous chains. Now, after the complete hydrolysis of amorphous domains, you can see that these nanocrystals lie parallel to the screen. And they occur as platelet-like nanoparticles. In the case of, this was for waxy maize starch, you can see the dimension, so the length is between 40 to 60 nanometers, the width range from 15 to 30 nanometers, and the thickness is around 6 nanometers. The process is quite different because starch, compared to chitin and compared to cellulose, is more sensitive to acid hydrolysis, meaning that the acid hydrolysis treatment needs to be performed at a lower temperature. And for this, of course, the duration of the treatment is much longer. You can see this optimization, 5 days compared to 45 minutes for chitin and for cellulose. You can see also the yield. It was optimized at 15%. It's very low. We'll see the reason later. Another important difference with chitin and cellulose is the shape of the nanoparticles. In the case of chitin and cellulose, it's nanofibers or nanorods. And the reason is that this material, chitin or cellulose, is a structural element. When a material provides the mechanical properties, it's always in the form of a fiber. Here, it's a storage modulus. The function is different. So we can just see here the stability of the suspension. So after 5 minutes or 6 minutes, 60 minutes steering, when using hydrochloric acid or sulfuric acid, as I told you previously, when using hydrochloric acid, the suspension is not stable. But when using sulfuric acid, and because of the sulfate group, which are introduced at the surface, the stability of the suspension is much better. So I will not describe this curve, but we can see the evolution of different parameters, like, for example, the percentage extent of the yield of hydrolysis as a function of time. I have a short video. I hope it will work, but I don't need to have the sound, just because it's a music which is not very good. And I'm sorry, but this video is not in English. It's not in French also. It's in Spanish. Because it results from a collaboration with some colleagues in Argentina a few years ago. I will briefly explain what is in this video. In fact, starch nanocrystals have been used to reinforce thermoplastic starch. So it's a starch composite. So it's a very good composite. And this gel can be used to coat fruits, for example. And it provides some mechanical properties, but also barrier properties. Because the diffusion of gas is very difficult because of these dispersed nanocrystals. And so it extends the lifetime of the food. And also, you can eat this coating or this packaging because it is starch. So you can see here Laura, which is coating the apple with this gel consisting of thermoplastic starch and starch nanocrystals. So many applications. I don't know if you can. For French people, it's quite easy to read Spanish, but maybe not for you. But so it can be used for different applications, cosmetics and so on, or for the slow release of fertilizer also to coat food also. And so this is how it is obtained. So the starch that was used for the matrix was obtained from manioc, and the starch nanocrystals were obtained from maize. And so you can see the aspect of the food with the coating of or without the coating. So this is an explanation of the barrier properties. So the gas molecule can go easily in the film without nanocrystals, but when introducing these starch nanocrystals, there is a tortuous pass, and it's more difficult for the gas molecule to penetrate and to go through the film. So this is for the mechanical properties. So it's a biodegradable, comestible, so it's easy to understand. I don't know what is this fruit, maybe apple, I don't know. So it has been patented also. And so it has been patented for food, but also for other applications, like, for example, in cosmetics. No, again, so just to come back to the starch nanocrystal, so you have seen that the duration of the treatment is quite long. The yield is low. And this is due to the fact that because of the long duration of the acid hydrolysis treatment, during the first day, some nanocrystals are produced, but during the extended hydrolysis time, they disappear. They are completely dissolved, even if they are crystalline. And we can see this here. You can see after the first day or up to the day 5, some nanocrystals are obtained and some granules remain. So different strategies have been used or tried to extract the nanocrystals that have been formed during the first day of the acid hydrolysis treatment, but it was not really successful. I will just show you one. It consists in an enzymatic hydrolysis pretreatment of starch granules before the acid hydrolysis treatment. You can see here the aspect of the starch granules with different enzyme activities, and you can see that after 2 hours enzymatic treatment, some holes appear on the surface of the granules, and what we expect at this time is that it should facilitate the penetration of the acid, because in this holes, of course, and then facilitate the dissolution of amorphous starch. And so this is another example in which different enzymes have been used. And finally, so it was good because you can see the evolution or the extent of hydrolysis here. It's a function of time. And when using this enzymatic pretreatment, we can see that we can reduce the duration of the treatment. So this is just to show you that there is an impact also of the starch source, because we have three different crystalline types in starch: A type, B type, C type. If I remember, A type is mainly for cereal, B type is for tubers, yes, I think, and C type is mainly for beans. And in fact, we have a different crystalline organization of this different starch, and you can see that it results in different shape for the starch nanocrystals. So they are more square in the case of A-type starch, and in the case of B-type starch, it's more like spherical particles. So I think it's time to conclude. There is a growing interest in both the non-food usage, of course, of renewable resources, but also in nanotechnology. So polysaccharide can be good candidate for this because they are low-cost material, they are abundant, they are renewable. It's possible with this polysaccharide to prepare nanoparticles with different morphologies. I mean long filaments, nanorods, nanoplatelets, and different aspect ratios. So the aspect ratio refers to the ratio between the length of the fiber and the diameter. Of course, to have a broader application, it's necessary to produce advanced and cost-competitive nanoscale product from this polysaccharide. The field of technology can be alarming and generate many ethical questions about environmental and health risks. So, of course, many uncertainties associated with nanoparticles and some of their use remain. But you have to remember that if I take as an example cellulose nanocrystals or cellulose nanofibrils, so they are obtained in an aqueous dispersion. And so they are well dispersed in this in water because of residual hemicellulose on the surface in the case of nanofibrils, and because of sulfate groups in the case of cellulose nanocrystals. Now, when drying this suspension, it's no more in the nanoscale because this nanoparticle aggregate, meaning that the risk is probably limited. So thank you very much for your attention, and sorry for the small problems that we had at the beginning with the video. I don't know if you have any question.
The session is open for questions.
Professor, so I have one question on this separation process, because end of the day, after acid hydrolysis, both micro and nanomaterials are exist in the systems.
Yeah, you mean for starch nanocrystals?
Yeah, starch nanoparticles. So if you look at commercial point of view, what kind of separation techniques we can use for this?
I don't know. In the case of cellulose nanoparticles, nanofibrils, and nanocrystals, these nanomaterials are commercially available, meaning that some optimization has been performed. In the case of chitin, I don't think that there are some commercial products, but I have been contacted by a company in China 2 years ago, and they plan to prepare chitin nanocrystals. I don't know what it is now. They ask me if I'm ready to work in China. I say no. And in the case of starch, for sure there is nothing. Now regarding the strategies that have been proposed, it was not, no, it's not described here. I have to remember We try selective permeation of the nanocrystals, so they can only pass if they are at given particle size, but it was very difficult because the starch nanocrystals that form usually aggregate on the granules, and so they are very difficult to separate. We tried some other strategies. I don't remember which one, because you can see that it was Deborah Lecor, so it was a defender thesis.
Centrifugal process can...
Centrifugal, exactly, we try also, but we had the same problem. The small nanocrystals are adsorbed on the starch granules. And I don't know if we try some, no, I think it was the two main strategies that we tried, filtration and centrifugation.
Okay.
Yeah.
Okay. But that will be interesting, because if you look at commercial point of view, separation would be a bigger challenges in terms of making this. Yeah.
Yes. And the duration of the treatment also.
Yeah, that's true.
And the yield is very low.
The cost end of the day. Yeah.
I don't know if we will see some commercial production, but it's not my job.
Yeah.
It just shows that maybe we can do something.
Thank you so much.
Any more questions?
Professor, this cellulose are available in all trees, right? Whether the mechanical properties will differ from different sources or is constant?
Sorry?
The mechanical properties of cellulose available from the plants.
The nanoparticles?
Yeah.
Yes.
Will it be different from different sources of this cellulose nanoparticle?
If it depends on the source of cellulose, no, I don't think so. I don't think so, but there is a broad range of values, which is mainly due to the experimental condition. But if you consider cellulose nanocrystals, extract from, I don't know, cotton, extract from rami fibers, extracted from rice straw, it's the same material. It's a cellulose crystal. So meaning that the mechanical properties should be the same. But what we will see later is that the reinforcing effect can be different when adding these nanocrystals or nanofibrils in a polymeric matrix.
Thank you.
But for the individual nanocrystals, it's the same properties.
What is the shelf life of the cellulose nanoparticles? Because
I'm sorry, can you come here, because of the air conditioning, it's difficult to hear you.
what is the shelf life?
More. Come here. And use the microphone, please.
Because already this is hydroscopic and biodegradable.
Is hydrophilic? No. Biodegradable, yes. Use the microphone, please.
Fungal will be attack fast.
What is the shelf life of these nanoparticles?
Yes.
Because it's belong to microbial and the fungal attack, and maybe go for hydrolysis also.
Yes. Of course. It's a natural product, so it can be degraded. But this is maybe one of the objectives in using this kind of material.
How you keep this nanoparticle in a desiccator or separate any container? Where you keep the
How do you store this material?
It is stored in the form of aqueous dispersion, but it should be in the fridge. Yes. Otherwise, of course, you have some bacterial growth, and it should be in the fridge.
In the form of a gel or a solution form, or dispersion form, or a solid particle powder form?
What you can do also, sometimes you can add some drops of chloroform, for example, or to avoid this bacterial growth. Sorry for the second question.
Says what kind of form, whether it's a gel form, is asking, whether it's a gel form or it's a powder form, what would be the best mode of keeping this material of these nanomaterials?
In gel form, it's better. but I will explain this later, but it's better because you keep the dispersion or the stability of the dispersion in the liquid. Of course, this is a problem because usually the solid content is very low. So it's typically 2% or less in the case of cellulose nanofibrils, meaning that you have 99% water. And if you want to use this dispersion in another place, it means that you have to transport 99% water that will be removed. So, meaning that, of course, the best form is in the dry form. But you should be able to redisperse these nanoparticles, which is the case. You know, there are some manufacturers of cellulose nanocrystals or nanofibrils, and you can buy it in the dry form that can be redispersed. And typically, so the most well-known company is L04 in Canada. They add NaCl in the dispersion to avoid the aggregation, and then it can be redispersed in water. But in the lab, so usually it is stored in the form of a suspension, but in the fridge.
Thank you. Thank you.
Any more questions? So, considering if we are making a composite out of the nanocellulose fiber or crystal with another nanocomposite or any other, another nanoparticle or any other particle, how can we expect the mechanical property or maybe a physical property or a chemical property change, whether the fibril or the cellulose nanofibers, will they dominate the property with respect to the nanoparticle which we have added into that for the composite?
When adding two types of nanoparticles in a matrix. This is the question. Yeah.
Yes.
And so the question is what happened or what is the most important?
I mean, how can we expect the change of the property, mechanical property, apart from a simple cellulose nanocrystal or a nanostructure with the composite made of cellulose fiber or a nanocellulose crystal?
In fact, so there are different papers where a mixture of cellulose nanofibrils and cellulose nanocrystals have been used. So I don't remember exactly what was obtained, but what you can do, for example, is to use both cellulose nanofibrils or nanocrystals and starch nanocrystals, because the function is different. In the case of cellulose, so it's long filaments or nanorods, what we can expect is improved mechanical properties. In the case of starch or starch nanocrystals, it's platelet-like particles. What we can expect is better barrier properties. And so by mixing these two types, maybe we can expect some improved mechanical properties and barrier properties also.
So if you're considering just one part, like the matrix be nano fibers and say a reinforcement is some other particle, say another nanoparticle, then will the nanofiber be dominating in the case of mechanical property?
Case, the cellulose nanofiber are the matrix.
Yes.
Yes. This is done also because, you know, you can form a nanopaper or film with these nanoparticles. So you can imagine that with starch nanocrystals, it's very difficult because it's not a cohesive film. In the case of cellulose nanocrystals, it's also difficult. It's also difficult because it's a short rod-like nanoparticles. But it's easy to form a film or nanopaper with cellulose nanofibrils. And of course, you can embed in this network some nanoparticles that provide some specific properties. It was done, for example, with cellulose nanofibrils and clay that was embedded in the material to have some specific properties, or you can also embed some active ingredient, I don't know, for the release of fertilizer or some chemicals and so on. But yes, cellulose nanofibrils can be a good matrix because it's a cohesive material.
Any more questions?
Thank
So
you.
we'll conclude the session. Thank you, sir.